Hey folks, welcome back to the show. Today we're going to be following up on the conversation that we started with Jane Harriman about JuliaCon 2020. We have Nate and Molham today, and they're going to be discussing what I originally thought was something of an application of AI to data science and using Julia for a data science project, but actually upon clarification, it's much more software oriented and a bit of a deviation where it's a technical challenge that many people might be trying to solve, for example, with like C language or Rust or something like that. But instead they're using Julia for it. And I thought that was interesting, and it can really spur a lot of good conversations. So again, it just shows that you can get something wrong and still learn a lot. So I will be serving as that sort of, I guess, intellectual whipping boy today as I get my perspective changed on this. So welcome both of you. Maybe we
Thanks.
could be, yeah, maybe we should begin with you each introduce yourself. We'll start with Molham and just your general background area, and then we'll get into a bit more of the technical specifics.
Sure. I'm Molham Aref. I'm the CEO of RelationalAI. I'm an engineer by education. I've been doing machine learning and AI type stuff for almost 30 years, but mostly in an enterprise context, working with big companies and helping them solve supply chain problems or fraud problems or wireless network optimization problems and things like that.
And I'm Nathan Daly. I've been a software engineer at RelationalAI for just under 2 years. We met at JuliaCon 2 years ago, and JuliaCon's been a great place for making connections with lots of people in the Julia community, and that's how I wound up here. And I'm at RelationalAI. I'm helping to work on building the database product that we're building here.
Cool. Before we go into the technical details, maybe Molham, you could tell us a bit about the application background to this, so we can sort of get our bearings straight.
Sure. So having been exposed to this class of problems for a long time, and having had to use the traditional tools that are available in terms of traditional databases, traditional programming languages, traditional tools for analytics, for machine learning, and data management and data transfer. So over the years, we realized that the process is just too hard and too complex. The problem doesn't really stop when you finish building the model, because that model typically has to be deployed in a way that a business can use. So it's not enough to have a model that can tell you fraud or no fraud. That model needs to be deployed in an overall system that plugs into the machinery that you use when you use your credit card, that scores every credit card transaction, that can flag each transaction as likely to be fraudulent or not. And if it's likely to be fraudulent, it needs to direct the transaction to some workflow where there's some banker looking at the file that comes up and looks at it and says, yeah, this is a fraud, we want to stop this transaction, or we're not sure, but this is a really important customer. So anyways, there's a lot of complexity in the whole process, and we feel like the system that we're building is going to remove a lot of that complexity. And we love having Julia as a foundation for what we're building, because Julia makes the system that we're building easier to build. So simplicity is hard to achieve, as we all know. And so having Julia as a foundation keeps our system simple, which means that the system that we provide our clients is also very simple, fewer moving parts, a lot less things to worry about. So that's at a high level what we're doing.
Yeah, that's really cool. And I guess because one of the things I think has really interested me as I've gone into more of the industrial role and gone from sort of the academic research into more of a industrial setting is uh, there's this sort of this I call it sort of like full stack data science, where typically a lot of the research and the model building happens in one sort of very specified confined domain or space. But there's this sort of full stack of technologies that are necessary to actually make sure that this thing gets deployed and used optimally. And then also to how to track how people are actually using it. So there's a large number of issues, just the ergonomics of making use of a model, seeing how people are interfacing with it and things like that. And then not to mention the challenges of making sure that something being that once it's been deployed, that it's staying relevant and useful and things like that. So, the idea that models can deviate in time for what their intended purpose was, what their intended or sort of estimated performance, things like that. So I think that this is really interesting, and actually, it's something that on the series we're going to be trying to cover starting in next year in 2021 on full stack data science. So maybe it'd be cool to have you guys back on to discuss that further. But so maybe Nathan, you could tell us a little bit more about sort of the traditional technical approaches to resolving this problem, and then why Julia is offering you sort of an attractive tech
Yeah.
stack to solve this. Yeah.
Yeah, happily. So yeah, like Molham was just saying, we're the product that we're building is ultimately is a cloud deployed database and knowledge graph management system. So users interact with our system by uploading their data or making their data available to our cloud database, and then writing complex programs and queries that can take advantage of that data and learn or derive useful, interesting, actionable results from that data. And so the sort of the technical components of that, like from our end, are we have to build a web server that can handle requests from users. We have to build an entire database management system, which is a very non-trivial task that in software engineering is databases are really interesting. I guess they hit a lot of the sort of interesting things in computer science. They're sort of all ticked in a database management system. So we have to have really good control over our access to reading and writing from disk. We have to have really good access to transferring data over the network. It's a big distributed computing problem when your queries get too large and you have these complex operations you want to do. How can you shuffle that across many machines? And there are also really interesting compiler and language optimization problems because the user specifies what they want to compute in a query, where you say, like, I want to get all the information from my database that matches some criteria, but there are many different ways in which you could actually go about doing that process. This is like translating the user's declarative language specification for their query into an imperative program that we then execute. And so there's all these very interesting challenges. And so traditionally, of course, database management systems are built in traditional computer science language, software engineering languages like C, C++, Java, C# maybe. And more recently, I think the trend is moving towards things like Rust, where there these emphasis on static compiling and safety and a higher level language facilities. So this is definitely, I think, abnormal to take on a project like this in Julia, but actually Julia is really attractive to us for a whole bunch of reasons. So I think there are sort of like maybe three separate tracks that you could talk about for why it's attractive to us. But I would say the main one is what Molham said, which is that it's just a very nice, friendly, high-level language to write in. So it's just productive. It's easy to write Julia code. It's a nice, attractive, simple language to express very complex ideas in, and it based on some clever design decisions in Julia, you can write the same kind of high-level code you might write in Python or MATLAB, but it's able to, by taking advantage of the static typing, by taking advantage of the static type information at runtime dynamically, it's able to still, on the fly, compile your code down to very efficient machine code in the same way that C++ or Rust would do. So you sort of get a lot of these benefits of writing in a high-level language like you would in Python, that just makes it easier to program and easier to reason about your code, while not having to sacrifice the speed benefits that you get from these traditional statically typed languages. And so I think that's been I would say that's the main driver of why we settled on Julia, is that it's, among all the other options we tried, it's just the most productive. And then the other two are a little more technical, but I think
actually,
the one that...
before you go into those two, because this reminds me of a conversation that I've been having with a number of people, especially about essentially understanding what language you're going to be using for your data munging processes and things like that, organizing your data and things like that, because obviously there are a lot of older technologies that are extremely capable in their own rights for specified tasks and things like that. But one thing that I've always been trying to sort out in my head, and I say I'm trying to sort out because I lack certain of the technical expertise on some of those on those more computer sciencey aspects, about database processes and things like that. But one of the sort of challenges I see is that people basically are wanting to do more complex interactions with their databases. They are wanting to sort of engage with their databases in these more, I guess, downstream data sort of interactions and processes. And by working with a sort of, I guess, just to choose a little bit of a we could call it a whipping boy, so to say, like a SQL query, and people want to do a lot of things just in SQL. Where SQL is actually an extremely good language. No one should beat up on it because it is impressively like capable at certain tasks. But there's also issues where when people are trying to, for example, do a lot of analysis or further data management in SQL, that you can actually lose transparency about what's being done in the data, and particularly as the data sets are not as consistent. So, for example, say you have a data set that's created on one purpose, and then you have a 95% similar data set on another one. That extra 5%, by losing transparency via, for example, the language that you're using, you could actually start creating data errors down the line that you're not aware of. And well, I realize that this isn't explicitly or maybe this is part of the issue that you're dealing with, that there's an element where, for example, you might actually be more comfortable doing your data munging in a language like Python because it's a bit more transparent, and you're willing to take that performance hit. And it sounds like by working in Julia, you're able to have that sort of that higher level of transparency, that higher level of complexity, without losing the actual performance too. Is that sort of the issue, or one of the issues here?
Yes, I think there's like so many things we could talk about, and I totally love the idea of having us back one day in the future to dig more into working with data at scale in industry, because even this problem that you just described, I think, is actually very much on our roadmap so actually one of the things that we're building here is a part of our database management system is we're building a new query language, a programming language, which you could use in addition to or instead of SQL for writing your queries over your data. And we think it actually addresses maybe a lot of those concerns you were having, in that this language that we're building internally is itself as powerful as Python or Julia. It's a full Turing complete computation language. So it maybe gives you some of those. So with the goal being exactly like you said, so that you don't have to switch in between all these different complexities in your stack, like Molham was talking about. So you want to use the fast database for doing this part of the thing, but then you lose these trade-offs, and now you have to go and do this. You pre-process your data in Python first, because you know how to you have libraries in Python that you can use, and you get more control over the kinds of things you're doing. And once you're done, you load it into your database, and now you can use the power and the speed of your database, which has been highly tuned for the complex types of operations you're doing. We don't like that either, because like you said, it's a complex system. It's too many moving parts. It's fragile. Little data problems can creep in, et cetera, et cetera. So the query language that we're building, the programming language that we're building internally at RelationalAI, it bridges this gap, in that it's the same language that you can use for doing these queries that are going to be really fast and highly tuned. But you can also do your data munging and your operations on them all in the same system. And the reason that this works is actually the same reason that it works in Julia. And so now I can go back and answer your question. So both because we're built on top of Julia, but also because the work that we're doing just works with the same principles that Julia is built on top of, we get the exact same benefits. And the reason for that is that there is nothing special cased in our database management system. So in something like Python, if you get the high level language of Python, which is really friendly, but it's slow and it's a known thing. So what people do to make Python usable and fast is they take the parts of your system that are the core of your computation, the hot loop, the main bulk of what you're actually doing, and they work really hard to make that fast. So for example, NumPy is a library that's built in C++ or C, and it's statically compiled, and it gives you a set of operations that have been highly tuned for the specific task that you want to do with that library. And so in Python, you do the high-level connection of the fluid parts that NumPy wasn't able to give you operations for, because they didn't know in advance what your problems might be. And so you use a dynamic language to meet whatever your problems might be at runtime. And once you're done and you're ready, then you can hand that over to NumPy, or like you were saying, hand it over to your SQL database system, both of which are very specialized for the very specific thing that they do, and they do it fast. The problem is, of course, when the thing that you want to do, you also have to do it on a large scale, and there isn't a pre-compiled, pre-computed operation for it in NumPy or in or in SQL. SQL doesn't have the ability to have the insight into these things like you're talking about. So the way that Julia tackles this problem is that there is no difference between these highly optimized core nuggets and the high flexible, high-level language. Basically, they made a bunch of design decisions in Julia, which are easier to see in retrospect, that that allow the compiler to turn arbitrary high-level Julia functions into the highly specialized compiled code that NumPy would do. So basically, Julia's trick here is it bundles LLVM, which is a compiler which compiles code from whatever C++ or whatever high-level language you write it in down to machine code. That operation is normally done ahead of time. Like in C++, you write your C++ code, then you compile it, and then you get a machine program, and you execute that program. The compiler is actually bundled as part of Julia's runtime. And so when you're about to execute some code, only at the very last minute, when you're finally about to do that hot loop, and you have all the context that you need, you know in what context it's going to be used, you know what the types are going to be, you know what the output is going to be going into, right at that moment, you compile everything, and then you execute it. And so what you end up with is you still execute little tiny kernels, just like you would do in NumPy. You execute this little tiny kernel for the operation you want to do, and then you ship it. In this case, you're still precompiling little tiny kernels and executing them, but you delay that decision to generate that kernel until the very last minute when you have all the information. And that allows you to get just as fast code as you would have gotten by writing it ahead of time in C++, but you get it for your specific problem at runtime in Julia. And so this is they call it just ahead of time compilation, because it's ahead of time compiled in the same way that C++ is ahead of time compiled, but it's done at runtime just before you use it in the same way a traditional JIT compiler would do. And so this is also called, in the programming languages world, this is called specialization, runtime specialization. And it's really neat. So it gives you the ability to write very flexible high-level language, but still see the fast performance times that you would get in something like C++. So finally, our system that we're building, RelationalAI, does exactly the same thing. So this is a big trend in databases these days. We're not the only ones to do this. Query compilation is the term in the database world, where the user specifies the query that they want to run, and you maybe don't have a specific nugget already pre-built for the operation, but you actually turn the user's program into you turn the user's query into a high-level program, and then you compile that to disk, and then you run it just in the same way we were just talking about. But for traditional database systems, for other database systems that do this sort of thing, maybe I'm not sure if I can remember the names of them, but databases isn't my background, but this is all stuff I've learned after joining. The way this is done is actually like you compile the user's query into a C++ program, and then you write that C++ program to a file, and then you call GCC, and you have GCC compile that C++ file into a program, and then you run that program over the user's data, and then you throw the program away, and then you send the data back. And that's like just what you do every time the user issues a query. And so this gets us to the second reason that we chose to use Julia, and this is because we also want to build a runtime compilation engine that can compile the user's queries just in time, just ahead of time, to take advantage of all the context that we know about the user's data and the user's query. And instead of having to build all that infrastructure ourselves, we just let Julia do it for us. So we not only used the Julia language to build our database management system. But then also at runtime, when the user gives us a query, we compile that query into Julia. And so we target Julia as our compiled language. And then we let Julia compile that at the last moment all the way down to machine code, just like it would normally. So hopefully that's a lot of information, but.
Nathan, just a thing to clarify,
Yeah.
the process you described where, you emit a C++ program that you then send to GCC, that's what Redshift does. So some of the people listening to this podcast might know Redshift. It's Amazon's data warehousing database. Most databases actually interpret the query. They don't even attempt it. So, and they suffer from all the ensuing performance problems that you have when you're interpreting, which is what you see, for example, in native Python code that doesn't call the process interpreted and stuff.
That's right. Yeah, you're right. I was already giving maybe too much credit to the standard databases out there. That's right. So like I think most databases, you could think of them as exactly like you said. They're like a Python. So you issue your query and they're interpreting it just like Python interprets it. But the hope is that the most important work that you're doing in your query happens to hit these fast paths that they've already compiled an efficient nugget for. And that works really great. But the moment that you want to do a more interesting query that doesn't fit within one of those pre-compiled fast paths, you're suddenly slow and you don't know why, and it's very difficult to understand the performance trade-off. And so we don't have any of those problems because foundationally, we're built on this just ahead of time compilation dynamic specialization like Julia is doing, which is really cool.
Yeah, that is really cool. And it is nice that, when you spend, for example, someone like me who basically spends 95% of his time, I'm going to say analyzing data, but it's more like pretty much just organizing it, munging around and just trying to figure out like how to even organize it and plotting it and things like that. But there are a lot of elements in sort of the data, we'll just say handling process that people who are just simply oriented towards the analysis of the data, essentially we have to take them for granted. And as you said, it is something where essentially we write up what we want, we let it fly, and we hope that whatever we want is actually conducive to computational efficiency. And we are pleasantly surprised at moments that it is, or alternatively, we don't even think to wonder at all. And then the times when it suffers, we sort of just take that as, a fact of life. And it is really nice that there are these peripheral and support elements, and there are strong computational reasons why these challenges arise. And of course, we can't expect every data analyst, every data scientist, every statistician to appreciate the full depth of these problems. But at the same time, it is nice to recognize that they are there and that we have friends out there like you guys who are actively trying to solve these problems and interfacing with the data in a way that we frankly would actually prefer not to even bother thinking about. We'd like to spend our time focusing on other things and have you guys handle that stuff. And so that is very helpful. One question that I'm curious about is because we have talked quite a bit about what the user might want. Who are, if you don't mind me asking, who are the users? Like who are sort of the use cases where they can really make the most of this?
Most of our customers are ultimately going to be big companies. So we're working with a very large retailer that's using some of our technology to enhance search and recommendation on their website. This is a top 5 largest retailer in the US. We're working with a large software company that develops software for taxes, for taxation. And the software is used by some of the largest companies in the world. We're working with companies that are in the Fortune 100 that have hard problems around fraud detection and around infrastructure management, connecting with their consumers. So at the corporate level, those are our customers. Now, inside those corporations, we're working with technical people who come from 3 communities. They're either business analysts and people well-grounded in SQL, and they want SQL and tables and their favorite business intelligence tool, BI tool like Tableau or Excel or something like that. We have another community of data scientists that are very much about tensors and linear algebra and notebooks and using things like that. And there's a third community of people who like to use graph technologies, and they like to think in terms of graphs and navigational query languages and ontology modeling environments and so on. So from a technical perspective, you have those three users. And from a business perspective, you have large corporations that are trying to improve decision-making in some way or automate decision-making in some way inside their companies.
Yeah, I really like that the idea, again, that there are so many services that are popping up to help, for example, various people around the sort of data scientist, data analysis area. While we're at it, should we talk maybe a bit more about knowledge graphs and what people are trying to precisely resolve with those issues, and what are some of the challenges too?
Yeah, so knowledge graphs became a thing in 2012. Google announced the Google Knowledge Graph on May 16th, 2012, which happens to be my birthday, with a blog article about things, not strings. And the idea is that you start to sort of manage information in a more structured databasey type way. And the Google Knowledge Graph is actually deeply baked on a lot of things that Google does. The search engine, when you search for a city or a person or a university or whatever, you will often see a box appear on the right-hand side of the page that will tell you for a person when they were born, when they died, how many children they had, and other information that basically is a result of running a query on a knowledge graph, which is, as Nathan said, is just a database that's structured in a certain way and giving you back the results. But the Google virtual assistant and many of the Google services also incorporate knowledge graph. Amazon has and it talks very loudly about the Amazon product graph and product knowledge graph. They also use that as a technology that underpins many of the things that you do, not just search and recommendations on their website, but Alexa, Prime. If they, for example, sell you a CD, Taylor Swift, the knowledge graph contains information about the CD and the songs and so on, but they also know about Taylor Swift, the person, where she was born, and other things about her. Apple, of course, has Siri, and if you go look at Apple job postings, you'll see that they're hiring for product managers and developers on the Siri knowledge graph. When you ask Siri, how's the weather outside, it's actually taking that speech and translating it into a query that runs against the knowledge graph and gives you, the answer to your question. And of course, you can ask somewhat involved questions, and it connects the dots. But in the end, it needs to be able to answer your question, and that question is translated into a structured query that runs against the knowledge graph. Microsoft has the LinkedIn knowledge graph. They call it the economic graph. They have the Bing Sartori graph, which underlies their search engine. They have the Office 365 knowledge graph. They have the academic knowledge graph. And you're starting to see sort of recent trends towards, Facebook talking about their knowledge graph, IBM talking about their knowledge graph, eBay talking about their knowledge graph, and so on. So there are a lot of different uses, and this theme is emerging, and we think knowledge graphs are the foundation for doing artificial intelligence in general in the enterprise. And we think it's actually the foundation for the software 2.0 movement. We think in the future software services or components or functions will not just be written by hand by programmers. Many of those components will be learned, like Google Translate went from being a million lines of C++ code to being 500 lines of Python that run a script on TensorFlow that basically learns mappings from any language to any other language. If they're not learned, if the components are not learned, they'll be declared. You will just sort of say, this is what I want. And as Nathan said earlier, when you ask a database, like, give me all the customers that are in the Northeast who have a middle initial X who visited my website twice in the last 4 weeks, you're not really specifying how you want that answer. You just say what you want. And so more and more of these services and software components are going to be written declaratively. And of course, that makes them easier to build, easier to maintain, easier to evolve. And historically, we haven't been able to declare as many of our software components because the declarative languages out there have either been not expressive enough, like SQL. You can't express everything that you want in SQL. SQL doesn't even capture polynomial time algorithms, or they're not performant enough. You just needed to be able to tell the computer exactly how to answer a question because on its own, it's not going to be able to figure out how to get you the answer efficiently. Okay, and so with the combination of the algorithms we've developed and the Julia that helps us abstract away or compile away, I should say, all the abstraction. So you start off with a very high level declarative statement, and instead of interpreting your way to an answer, you just compile it down to Julia, which then compiles down to machine code, and you can get the answer to a very, very tricky question very, very quickly because Julia made the cost of the abstraction go away.
Yeah.
Okay, so I answered more than your question about what are knowledge graphs, but I was trying to show you examples and show you why we think there's a trend towards having a knowledge graph layer in everybody's footprint, and over time, more and more capability and software will be developed with a knowledge graph as a foundation, because knowledge graphs make it easier to learn software components and make it easier to use to declare the components that you want to build, and once you declare them, they're reactive and so on and so forth. So.
Yeah, definitely. You did bring up some what I think are some of the most interesting prospects for not just like machine learning, but software in general. I think the sort of software 2.0 issue is extremely interesting. So Nathan, now just so you don't leave that one person hanging, what was that third reason that you just got to get off your chest?
Yeah, no, I think it's, we'll go quickly, but just so Molham was just talking about how a lot of our smarts in the product that we're building come from the algorithms that our colleagues have actually been working together with academics for 10 years or more now on, which really make this kind of optimization possible, where we can figure out how to turn your declarative program into a program that can be executed quite quickly in many cases. And so a lot of what's going on here is actually really novel and interesting algorithms. And so we employ a bunch of mathematicians and algorithmists, I don't know what even the word is there, algorithms people. And for them, Julia has been, I'm sorry, you're on mute again.
I believe they go by algaes.
Algaes, yes.
Yeah, I think it's algaes. You leave them in the sun, you give them nutrients, and eventually you can just skim them off the water. And
that is not wrong. Yeah, exactly.
Not wrong.
So yes, our algae friends. So for them, I think Julia has been a real joy, and that's been one of my favorite parts about joining this company. To see the way that they use Julia. So I think. I've heard Python described in the past as pseudocode that you can execute. It's like executable pseudocode. It's, it looks just exactly like what you want to say, and then you can run it. I would say that also is true about Julia, but I've heard Julia described rather as executable math. So I think it really, with even little things like just support for the Unicode characters, so they can write their, they can write the same exact, they read a paper and it has an interesting algorithm in it, and you can just rewrite the math from the paper. And it basically just executes in Julia the same as it would in MATLAB or Mathematica, which are two widely used mathematic-focused high-level programming languages, both of which suffer from being really slow, just like the same problem that data science has with Python. So this is the other angle, I think, that why we found such joy using Julia here is we have a bunch of mathematicians, and I think it's really fun to see them be so productive in a way that I can't imagine they would have had the same success if we were having to struggle through C# or C++. Just the programming gets in the way of the ideas, and I really don't feel like that's true with working with Julia here, which has been really nice. Native support for tensors, native support for arrays and matrix multiplication, mathematical symbols. And also, I think multiple dispatch, which is something that you'll hear Julia people talk about a lot, but it's really esoteric to outsiders, is this idea that's really closely maps with math. And the idea here, if I have like a couple minutes, is just that in traditional object-oriented programming languages like Java and maybe Python to some extent, there's this idea that an object owns its methods. So like you can have an abstract type, which is like an animal, and then you have a dog, which is a type of an animal, and a cat, which is a type of an animal, and all animals can make a noise, and so dogs bark and cats meow. But the observation is that in mathematics, with most interesting operations, there's no owner of that operation. It's really what kind of operation should happen depends on everybody who participates. So if you're adding together 4 numbers and 3 of them are integers and 1 of them is a float, the integer doesn't own the plus operator any more than the float owns the plus operator. There's really no true owner. And so this object-oriented dispatch that we were just talking about is sometimes called polymorphism or dynamic dispatch. And in Julia, they call it multiple dispatch, where you choose which type of plus to do based on what all the runtime arguments are. And so this lends itself very well to writing mathematical operations. So you might say, hey, when I'm taking the Jacobian of a matrix, or I don't know linear algebra, but when you're doing some linear algebra operations and one of your things is a dense vector and the other one's a sparse symmetric, upper triangle vector, you should do this thing. And if there are different kinds of matrices, you should do this other thing. And you just write that once in Julia. You don't have to figure anything else out. You just say, hey, here's how this operation works when these are my types. So that sort of mathematical fluidity, I think, has been really, really a lot of fun to write Julia in. So that's the last thing I want to say on that.
No, that definitely is a really cool distinction. And I do appreciate that you've sort of held our hand through some of these more computational issues. Because, when you aren't quite familiar with them, it's a huge amount to, obviously it's multiple fields in its own right.
Actually, one more thing on that. I think the reason that Julia has found such success in the scientific world is that it feels a lot like Python, and you can just sort of start using it without caring about anything we just talked about, right? It's an easy high-level language. You can just write interesting data science tasks. You're like, I just want to do some machine learning on my data. I just want to open scikit-learn, get a linear regression and move on. But then when you do hit those cases that are actually the pain points, like we talked about earlier, and you don't know what to do, in those times you can then go and learn a tiny bit more computer science in this one moment, just for the one specific problem you have. And Julia lends itself so nicely to that. So I think it's a very friendly introduction into the gate, but it scales infinitely with the complexity of the task that you want to do. So in those places where you have a hard problem, you can either find a package that solves it, or you can write a package that solves it, or you can write code yourself. And that's something that you don't get in most other high-level languages. Yeah.
Well, Nathan and Molham, I really appreciate you guys coming on today. I know we didn't really plan to go on like a tutorial on some of these issues, but I do think it is really helpful to have, technical experts like yourself come and, hold our hand and walk us through some of these things, because when you focus so much just on the data analysis, you take certain other aspects for granted, it becomes a bit of a mystery why certain things are odd or not working out or suboptimal. And it is nice having those things being presented to you pleasantly, as opposed to, I don't know, someone like a sneering database engineer or something like that, although most database engineers are real nice people. But I really appreciate you guys coming on and just introducing some of these new ideas. And I think this also doubles down on some of the topics that Jane Harriman was discussing about some of the advantages of these other languages. So thanks for both coming on. It'd be great to have you guys come on later when we have this more like full stack data science talk. And again, just simple learning examples to start building those little neural connections between these other aspects with the databases that we usually take for granted. Now, of course, if you haven't had enough of Nathan, he's going to be in JuliaCon 2020. So, which is, again, it's a huge conference. It's free. It's a great value. It's a really fantastic community. So don't miss out on that. The sign up link for JuliaCon 2020 will be in the description below. So if you want more of Nathan, the crowd cries out for Nathan. There's your chance. Also, just as a side note, if you go to Nathan's website, that's Nathan Daly, you can, and I'll just link that one too while I'm at it. You can see some really cool environmental applications. So if you're interested in some more like the climate study type work and just generally cool applications, Nathan has worked on a very broad range of different applications and just cool tech topics. So he is a full stack worker in many ways. But I think I've said enough. Nathan and Molham, thanks so much for your time today.
Thank you, Glenn.
Yeah. Well, and actually just want to also plug that I think Molham's going to be giving a talk at JuliaCon too, so you can you can catch both of us.
But especially Nathan.
From people from RelationalAI and JuliaCon. So.
Sweet, cool.
Yeah.
All right. And will they be on the same issues, or will you be talking about two separate issues?
Just different topics.
Perfect. All right, cool. Well, catch both Nathan and Molham at JuliaCon 2020. All right. Well, guys, thanks so much.
Thank you so much.
Thanks.
Bye-bye.
Hey folks, it's Glenn. I hope you enjoyed this episode of Pod of Asclepius. If so, please consider leaving a like, a comment, and hitting that subscribe and bell button. We're a small channel and every bit helps. If you have a department, a lab, or even just friends who would like this episode, definitely forward it along. I don't have any of those things, but if you do, you should definitely celebrate by sending them an episode. We've got plenty of episodes on healthcare topics, particularly in data science and machine learning, so check out the other episodes on the channel, or some of the playlists. You can also check out our website to join our mailing list, or see our sponsors. Thanks so much to our sponsors for their support. And while the views discussed on the show are undoubtedly scintillating, they don't necessarily represent the views of our sponsors, the speaker's employer, my views, your views, my neighbor's cat's views, your cat's views, or anyone else not saying the words. In fact, they might not even represent the speaker's views by the time you're hearing it, so be sure to subscribe in case they come back onto the show to change their mind. See what I did there? Thanks again.